Go.
Does that make sense?
Therefore, y equal. Yep. Beautiful. How many people are happy? Yep. I was happy. Yep. Go. Okay. Up to you guys. How much time we got? Does that look right? Yeah, that looks right. Up to you guys. Do you want to do another one of those as practice now, or are we okay?
I'm fine with that one.
We're okay? Okay. Cool. 18 paper. So, this might be a familiar sort of question. I want to fill this flask with water. Right? I'm going to pour in, or I'm going to put it under a tap and just turn the tap to a certain amount, so a fixed amount of water is coming through per second. So, I want to draw a graph of what that looks like in terms of time going this way and the height of the water in the flask going that way.
It'll be a good.
Okay. That's a nice vague thing. I could draw many kinds of curve. Okay. So take a second, draw out what that would look like. No scale or anything, just the curvature of it is what I'm worried about. Yep. Go, Jacob's done. Yeah? Yeah? Okay, good one. Cool. Let's see what happens. 5. Who's 5? 1, 2, 3, 4. Celestia is 5. How are you going to draw this curve? Just rough. Just draw it in the air. It's easy. 2. Okay. So you're saying like that? Is that what you were saying?
Yeah, sort of like that.
So sort of like that. Okay, correct me. Which part? So I've got first part, second part, third part. This is how I'm just going to describe it. Which part needs adjustment?
Oh, that's just how I do it. Just like that.
Just like that?
Please bring me this one. I can do this one.
TJ wants to do this one? No, you've already had fun, TJ. You've already got the perfect round. 6. Jesus. Where's that? Is that right? How do you want to draw the same or something different? Okay. You want to draw something like that? Yeah, sort of. Tell me where to make adjustments.
Probably more steeper. It just depends on scale, though, so it's fine.
Oh, so you use the argument steeper? Okay. Well, yeah, we'll leave it like that just because steepness is just an argument about scale, as you said, so it's okay. Anyone else want to make a different version? Yep.
So like that, but then at one point it ends up just go like that, but then at one point it goes linear.
So going like that, and then at some point it goes linear?
Yeah.
Like that?
Yes.
Okay, we've got a couple different versions. This is interesting. Anyone else want to add one? Just be a little different? No? Okay. Okay, are we all certain that it's not going to be linear?
Oh,
Yeah? Okay, I agree with that. Is it going to be filling faster early or late? Late. If it's filling faster late, would that mean a steeper graph or a shallower graph?
Steeper.
Steeper. So when we get to the late time, it should be getting steeper. Can we rule out at least one of these?
Bubble one?
Purple one, why?
Because it starts off steep and goes.
Right, for some reason it goes steep, then shallow, then steep again. Right, so this one can't be. Can we rule out anything else?
One.
The red one, why?
Because it
So
starts
you can
off
rule out
steep.
your own one, that's good. Right, why?
Because it gets, as time goes on, it gets.
Right, this is the reverse curvature of what you want. So not this guy. So it is this, but you did have the correct addition at the end. We should have, this last bit should be linear. Right, because it's not changing width, so it should fill up at a constant rate from that bit. Cool. Okay, so we should get something like that. It is kind of critical that you can do that line of thinking, because this is the best way to save yourself from making dumb errors math-wise later. Right, because you can just see these curves. And if you can see the curves, you already know roughly what you should end up with. Cool, okay. So something. It is very common to get the reverse curvature, right? So I highly recommend go to the extreme ends and go, okay, where should this thing be steepest? Where should it be sharpest? That's usually what we're ruling out. Beautiful. Good, so we've got this, great. So I want to ask this question. What did I want to ask in the end? Forgot.
Why did I do this?
Distracted myself. Good. Oh, right, okay. I wanted to say, okay, we're going to define this function. Space-wise, let's say this is frame. What does that look like? So this is it. I'll just take this thing. And so start to keep those. Let's give them specific numbers because we're a little bit too general for mid-year 11 at this point. Let's say 10 seconds. Maybe that's going to get too big. Oh no, we can sort of yeah, sorry. No, we'll make those straight, otherwise it's going to get a little away from us too quickly. And we'll say that this is okay. Beautiful. Okay. Let's say I've got that. Okay. I want to figure out how quickly this thing is filling. We okay with that? Okay. Can we figure out how quickly? Oh, sorry. Take a step back. What would tell me, like what mathematical idea would tell me? Oh, I should also put it in. What mathematical idea would tell me how quickly this thing is filling after 10, I'm just going to say seconds. So this is in seconds.
Alles moet de stap niet dat
I would say it's in millimeters. It's similar, it's all related. What tells me how quickly it's filling?
Maybe the gradient.
The gradient, right? The gradient of this last bit. Cool, what is the gradient of this last bit? Don't know yet, right? Do we have a variable assigned to it though?
Yes.
What?
10, 100.
M.
Oh, yeah, sorry.
Yeah, because that's the gradient of the straight line.
Yeah.
Cool, so the rate that we're after is M. So ultimately we want to solve for it.
Mm-hmm.
How are we going to get M?
Try and do the video for
Okay, why? You're right.
because we're trying to find the gradient at a single point, and
Yeah.
because we don't have any other variables, it's our only option that we
Beautiful.
presented with.
So at this point, this thing connects smoothly. Right, how do we know that it connects smoothly?
Because of the flaws.
Because it's because of the
No, because of the flaw, like the shape of the flaws.
Right, we know that this thing is approaching this width, and and we know that there's the same amount of water going through it, so this would have to be a smooth transition. If it's a smooth transition, that means the gradients are the same. Cool, okay, so the gradient of this thing is the same, so that's going to land right on top of that, is the same as the tangent at that point. Okay, cool. So what I want is this blue gradient. Well, that's going to be when my function derives at, well, actually, sorry, we should get a derivative first. Do I want to derive the first part or the second part?
The second part.
The second part? Okay, let's call this F1 and F2.
Oh.
If I call that F2, what do I get when I derive it?
And
M. Is that useful? No, we'll just answer that question with the variable. If I go F prime of 1, what do I get?
2, 2.
Oops, there shouldn't be X's, there should be T's.
Oh, here's
Cool. Beautiful. Okay, great. Now we established that these two things have to be equal. Okay, great. Well, we've got that. They're equal all the time? When?
when the point is 10, 100.
Right. Specifically
Oh,
at 10
when
seconds.
Yeah, sorry.
Cool, okay. Do I know what this value is when t is 10?
No, you can figure it out.
Yeah, 2 times 10, 20.
Yeah.
Therefore,
That
M
means
It's 20.
is 20. Beautiful, done. What does this 20 mean?
That's the
average rate of
An average rate of change? What do you mean?
That's the run of the run.
The rise over the, okay, yes, it's the rise over the run, so graphically it's the rise over the run,
Yeah.
true. What does it mean in terms of the original context?
it's going, it's filling up by 20 each.
Okay, it is filling up by 20. What? 20 millimeters. It's filling up by 20 millimeters per second. There we go. Right? We had rise over run, yeah? Rise, millimeters, over run, seconds, millimeters per second. So therefore, 20 millimeters per second rise when in the neck. Coco?
When in the neck, what does that mean?
The neck of the flask. It's called a neck.
What about the rest of it?
Well, okay, if you want the rest of it, where do you want? Is it the same everywhere in the rest of the flask? No. So everywhere else in the flask, it's 2T. Yeah. Yeah.
Oh, okay.
But because it's consistent in the neck, we can say, oh, it doesn't matter where you are in the neck, it'll be filling 20 millimeters every second whilst you're in the neck. Cool. Is that true forever? No. When's it going to stop? Once it reaches the top, yeah? So this thing presumably should actually say I'm just going to call this capital T because we don't have a scale.
What are the
Oh, better yet, actually, let's do this. Let's say that this thing is 40 millimeters tall there. So if that's 40 millimeters tall, when does the thing end?
The 40?
Oh, no.
Wait, is that whole thing 40?
The neck is 40 millimeters. Right?
Oh,
Millimeters, sorry, not millimeters.
140 millimeters.
This is just 40 millimeters.
Yeah, I know, but the body is 100, is it not?
The body is 100, yes.
Yes, so when time,
Okay, so this is 100 millimeters. How did we know that?
because our graphically.
Right, our graph told us that at time t seconds, that's when we're at 100 millimeters high.
That's when we reach the neck.
Right, that's when we reach the neck, because that's when it goes straight. So this must be 100 millimeters tall.
Wait, did it say that that's when it reaches the neck?
So, okay, we've got the curve, and then it goes straight after 100.
Okay.
So that must mean that this is when we're at 100. Cool. Okay, I'm then going to tell you that it's 40 mil tall. How long does the thing keep filling for?
400 seconds.
2 more seconds, right? Because I'm filling it 20 millimeters per second. I've got 40 mil to fill. I need 2 seconds to fill. So when does my time end?
12.
12. Because it's 2 more than the 10. Okay?
Where did the C go?
The C.
Into the C.
Okay, so, well, we can figure out that C if we like, so that's going to be down there somewhere. Okay. What do we got? We've got the point 10, 100, and M equals, was it 2? 20. Cool. Therefore,
What was it?
yeah,
100 equals
It's 1 times 10,
20 times 10, yeah, cool, plus C. C equals 100. 20. C plus minus something. Cool. Does that seem reasonable? Yeah, sure. We knew it should be somewhere in the negative. Is it, if I actually drew this, right, if I continue this down, would it look roughly at negative 100?
Yeah.
I'm going to say definitely no, but okay, because about there would be about 100.
Yeah, but your dashed line isn't exactly straight.
Okay, so this, whenever you do a sketch, right, was this thing carefully drawn to any kind of scale? No, so there's no way to expect that it should land anywhere, well, that it should land close, right? But it should be significantly negative. That's significantly negative, we're done. Beautiful. Was any of that math actually hard? No. Did people get confused in the middle of that though? Yes. What does that tell you?
They were stupid.
No, not that you're stupid. Right. This stuff can get confusing simply because you're going to be moving between context and the math. The math is typically not that bad after a little bit of practice, but switching between context and math and from math back to context can very easily trip you up. Always triple check your thinking when you're moving from one frame to another. Yep.
So, just to summarize how you did that equation, you just,
So when you say that equation, which one?
T to the power 2. Or you
Oh, I just invoked, I just said that that was that.
did, yeah, so did you just, figure out the derivative of that, which gives you M, and then that'll give you 2T?
Yeah. Yeah. So yeah, I gave you the ring.
Okay. And what was the MT plus C for?
So that was just to say that this bit is linear. So, which, you guys figured that out yourselves, that it had to be linear of some sort.
I was kind of dozing off or something.
It's all good. Beautiful. Okay. So now we've got this thing. Okay. What variables are in play?
Oh, there's M.
M. Where?
Yeah.
I say M.
We've got just T.
You got T, and at the very front,
Oh,
B. Based on what we were just doing, what is a plausible usage of, what's a plausible origin for this?
Volume.
Volume over time. Cool. Okay, so this is possibly, not necessarily, but possibly some volume over time description. Cool. What is this thing doing? If it's assuming that it's volume.
It's looking for the volume.
It's looking for the volume? It's giving you the volume. Right?
It's increasing over time, like a.
You sure about
Um,
that? It's decreasing. Why is it decreasing?
because it's a negative. Square.
Negative.
How about
Right? As
That's
t
right.
increases, this will get bigger, which is negative, and this will get bigger, which is negative.
yeah,
So what is this object doing?
Decreasing. So
Decreasing.
so you're basically spinning it all down.
Right, so maybe something's being poured out.
Or
Cool.
maybe something being drained.
Yeah, being drained, something like that. That's
Maybe something
plausible.
being drained.
Yes, possibly. Okay. Is this thing, is it possible that this is, say, a water tank and someone's just turned the tap on?
no.
No. Why?
Because that's a constant flow.
Right, that would have been a constant flow. Is this a constant flow?
No.
No, how do you know?
Because of the t squared.
Because of the t squared. So as time goes on, what's happening?
It's
It's
increasing in how much it decreases.
It's increasing in how much it decreases. That's true, but that is a really confusing way of saying it.
It's losing
the
more
more
than
time-
it is, it's losing more than it is when it's longer it takes. It's losing more the more it takes.
Are we noticing that this is difficult to say in English?
Yeah.
Yep.
The more time that passes, the faster the entity empties.
Kind of like
Okay, so that's a better statement. Cool. This thing is emptying faster and faster.
Yeah, that's
There you go. Okay.
all right. Don't need to flex on us like that.
But, so, this is the problem with moving from English to math, right? English notoriously lacks precision in the wording, right? Because I just say it's emptying faster and faster, that doesn't tell you much other than, okay, so the rate of emptying is increasing. But I don't know about how much, or if it's slowing down in that, or if it's speeding up in that, it doesn't tell you much. Okay. There's one other piece of information we can get out of this. How big is this object, or at least
600.
600, right? Now, do we have any units?
No.
No.
Yes.
Where?
No, I was going to say volume.
Over there.
Is it? Always? Not necessarily, right? Okay. Let's say this is liters and seconds. Okay. Okay, so maybe it's not a cup, maybe it's a tank.
Is it a volume or a depth?
Okay, so I've got this thing. Beautiful. If I now ask you, how quickly is this thing emptying? How would you figure that out?
Make T or something?
Make T equal something.
Would you derive the equation to find the gradient?
Okay, right, if I derive this thing, I could say that that's V prime T.
Yeah.
What's the other way of writing that?
Um,
So this is Newton notation, what's Leibniz notation?
Function of prime.
oh yeah.
Remember
Yeah.
that?
Oh,
Right, what is this telling me?
The derivative of v in terms of the derivative of t.
Yeah, okay. In a more English way, what's that telling you?
Oh, I don't know.
It just says, how much is volume changing for a time change? Right? Or in other words, if it's a change in time, how quickly? How quickly is volume changing? Cool. So Leibniz notation is handy because it tells you that sort of thing a bit more. This says the same thing, but you've got V prime T. Right? You can use either, it doesn't matter. But this is a little bit more explicit than that one, I feel. But you can do whatever. Cool, alright. So how quickly is this thing changing?
So it's minus t squared to the t squared over 100. Or is it just minus t? Minus 10t.
Minus 10.
If we derive 600, what do we get?
0.
Cool. If we derive negative 10t,
Yeah, negative 10.
Negative t.
if I derive this,
You get
1 over
negative.
100. 2t over 100.
alright, which I can simplify.
2, 1 over t over
Okay.
sorry, what does dv over dt
Mean?
like how would I use that equation to write down?
These mean the exact same thing. Alright, as far as we're concerned. These are just two different ways of writing the same thing. So it just means the derivative of the function v with respect to the variable t. That's all it means.
Which is the that. We just did that so we go
Okay. Cool, so we've got that, brilliant. Okay, so this thing is, it's all negative on the derivative, so it's definitely going down. Okay, fine. I forgot what else I wanted to do with this now. Oh, okay, so let's say after 10 seconds, I want to know two things. I want to know how much, let's just assume that it's water in a tank. I want to know how much water is left after 10 seconds, and I also want to know how quickly it is emptying. Okay? Cool, alright, so how much, let's just write it. How much water is left after 10 seconds? How quickly is the water falling?
No,
Volume. Draining is probably a better English word. Okay.
Pouring.
Yeah, pouring, draining, whatever. Cool, okay, so how much water is left after 10 seconds? How am I going to figure that out?
So, 10 to the
Into which equation I got two?
negative 10 minus T of.
No.
Shit.
Yeah, 50-50. Right. How much water is left? Which one of these talks about the water?
The top one.
The top one. What does the second thing talk about?
Talk about,
Right, how quickly it's changing, right? Do I want how much water or do I want how much water is changing?
how much
How much water, so I'm back at the first one. So this is equivalent to that, which equals whatever it is, I don't know. 600 minus 10 by 10 minus 10 squared over 100 equals 499, is that what you guys get?
Yes.
Yep, cool. There's something missing.
Those liters,
Liters, right, because we gave them units.
How many squares are around?
That's not right. That's the one. That's the one.
How big is it?
How big is it? It's that big. Like, I don't know how
Is
to
that
describe that to you.
is that depth or volume? I guess maybe that might be what you
What's your initial variable?
volume. Well, I know. I'm just saying it might be what he's asking.
Oh, okay.
It's about the size of this whole whiteboard.
Maybe they're big on.
What? How many dimensions does a whiteboard have?
2.
How many dimensions does a white? What? I'm not sure if you preempted my question or what happened there. Whiteboard, 2 dimensions, yeah? If you're talking about litres, you're talking about a volume. How many dimensions?
3.
Yeah. So saying, does it have the same volume as that whiteboard?
No,
That's
I was
really
picturing
weird.
if there was in like a box here.
Oh, if there was a box there. So how far? Okay. So if you had this and then you drew it out to however far, how far would I have to draw it out? I don't know. How wide is this thing? All that. That's about a metre by 1, 2, maybe 4 metres.
All right.
You're gonna go right in the corner.
There's a corner, there's a ruler out there.
I don't. No.
What's this? Let's
Like
say
1 by 4.
3, 1. What do we want? 49, 500. I'm going to call this 4 metres now, just to make life easier for me. So we need 20. Wait, it's 1,000 litres per cubic metre. So what did I say? That was 5 metres that way.
4.
Sorry, 4 metres. Sorry, 4 metres that way.
And then you said
I
1
need
down.
500 over 125. So, too many numbers. I need 125 multiplied by my 5 by 1.
4 by 1.
Give me my 500. Oh, my 4 by 1, sorry. Yeah. Cool, so that's how many. Oh no, that's it. Hang on. I want 1,000 metres cubed equals 1,000 litres equals 1 metre cubed, I think that's right.
Yeah.
Pretty sure that's right. This is, which way did I want? So hang on. 1 litre is 1/1000th of a metre cubed. I want 500 of these, so I want
That's 600, actually.
half a metre. I want half a metre cubed. Okay, so this, what do we say? 4 by 1.
Yeah.
So that's 4. I need to divide it by 8, so I need 12.5 centimetres coming out this way.
Oh,
So it's a bit of water. Okay. Roughly. Anyway, cool. Good detour. So, how quickly is the water draining?
that's using the second equation.
Using the second equation. Why?
Because the first equation is telling me about how much water there
Yeah,
is, the second one is about how much water is decreasing.
Cool. Okay. So I want V prime at 10 seconds.
So it equals minus 10 minus 10 to the over 10 over 185. 185.
50 equals, what's that? Negative 10.2. Sorry.
Wait, can you just do it in fractional? Like, is that possible?
Yeah, if you want, you can do whatever. What's this? Over 5 is 52. Is that right? No, 500.
Yeah.
So negative 500 and go over 5. You can do it that way if you want. Either, it doesn't matter. There's something missing though.
Seconds.
How quickly is the water draining? It's draining 10 seconds.
Liters per second.
Okay, so litres per second. And hopefully you guys are about to say the other thing. Yep.
No, isn't it
Squared.
just 52, not 502? That would be 100 and...
Where am I looking?
You did negative 502 over 5, isn't that just 52? Negative 52? How much times is 5 gone to 500? 100 times, not 10.
500, it should be just 500
Should
minus.
just be 52, right?
Oh, because I switched from 50 to 4. Yeah. So,
Yeah.
Yep. 10 and 2 fifths. Yep, got it. Yep, all good. Thank you. Cool. There's also something worth noting.
Actually, I think it's... Sorry, I think it's 1 2.
What?
Yeah.
Oh, 1 and 2, sorry.
Yeah,
come on.
So it's just negative 10 minus 10.
The number itself is what I'm getting at. Cool, that's a litres per second, not a 4. Cool, there's one little thing. If I ask for how quickly is the water draining, you would tell me,
In cubic...
I've got all the numbers up there, how quickly is the water draining?
Wait, what? This is sort of like 10.2.
10.2 litres
10
per seconds.
Okay, so
Square.
it's draining at 10.2 litres per second,
But it's
not negative 10.2. Right, what's this negative telling you?
It's telling you
That
that
it's draining.
That it's draining, right? So you don't need to say it when you actually answer the question. Cool, beautiful.
But if you didn't write negative... Oh,
So your calculation would yield negative, but your end answer should say
10.2.
10.2 litres per second.
like because your direction and your what's it called? Your direction and your direction going that way and your velocity. There you go. Yeah.
Velocity.
Right.
You said something about that, saying velocity going this way is
Oh, versus speed. Is that what you're talking about? Yeah, speed is just a number, and velocity can be a positive or
that kind
negative.
of applies to this.
Kind of.
But we're only not putting it in because the question is stating how,
It's already
how
stating
negative is it?
Yeah, exactly. It's implying the result is negative, but how negative is it? It's 10.2.
We should also
When